Okay, good. So what we need to do is we start off with the graph of an exponential y equal to 10 to the power x. Fill in this table of values and then draw the graph. Okay. Alright, substitute -1, you get 10 to the power -1, which is 0.1. Substitute 0, you get 1. Substitute 1, you get 10. Alright, so we'll draw the graph. Alright, so draw the graph. Put 1 here, and that's 10 there. And then very small here. So it looks something like this. So your exponential. Okay? Right. Have a try, draw it. And then write down the domain range. And fill in some. Okay, what will be the domain of this function? All real x, good. All real x. That. And what's the range of the function? Y is bigger than 0, good. And then furthermore, we can look at some limits. Is when x goes to -infinity, what does the function go towards? 0, good. When x goes to infinity, the function goes to infinity. Alright, so what we do is, so today we're going to learn how to differentiate this graph. Alright, differentiate this graph. That's a new type of function, exponential function, where the power is unknown. So in order to find the derivative and also the area under the graph, we need to use the differentiation by first principle. So let's write down the formula, limit h approaches to 0. Hopefully you still remember what this is. Looks like this. It's on the formula sheet. Differentiation by first principle over h. Right, so we'll try to differentiate it. So whenever we want to differentiate a new function, that's the first formula we'll go to, is to use differentiation by first principle. Alright. So what you need to do is, and very important at each stage, you always write limit again, h approaches 0. And then you calculate what f of x plus h is. Now f of x plus h means you replace that x you see there by x plus h. So it will be 10 to the power of x plus h. That x plus h comes from this, being substituted into the power. And then you subtract by the original function 10 to the power x over h. That. And after you do this, you're going to simplify it. We're going to factorize a common factor out. So write the fraction again. And using index law, we can do 10 to the power x times 10 to the power of h. Hopefully you can see that. When you add the indices, you multiply the two numbers, right? 10 to the power x times 10 to the power h is 10 to the power x plus h. I'm doing reverse of this index law. Minus 10 to the power x. No change in the second term. And then what we do is we're going to factorize a common factor. Hopefully you can see the common factor is 10 to the power x, which we are going to factorize out. Okay, lim h approaches 0, h, so you get 10 to the power of x factorized, 10 to the power h minus 1, like that. Okay, good. So we're going to make h approaches 0. So far we can't cancel h. Normally we can cancel the denominator out, but we can't in this case, isn't it? But what we could do is, because h approaches 0, it doesn't affect the x term, isn't it? So what we could do is to factorize the 10 to the power x out. You can take this out of the limit because it's not affected by the value of h. So write 10 to the power h minus 1 over h. So our aim is to calculate this limit. Okay. Now one way, well, what if I substitute 0? Well, if you substitute 0, you have 0, and the top will be 10 to the power 0, which is just 1 minus 1, which is 0 over 0, isn't it? We can't have 0 over 0. So what do? We have to use our calculator. Let's make h as small as we can to see what that limit becomes. So what we do is we're going to write this limit again at the bottom. We're going to do a table of values. So write 10 to the power of h minus 1 over h. We're going to use a calculator for this, making h as small as we can. So get out your calculator, type in this fraction, 10 to the power, so write fraction key first, and write 10 to the power of h. Now h is 0.01, so type in 0.01, and then out of the bracket minus 1 over 0.01. Okay, write down what it is. Correct to maybe 4 decimal place, so 2.3292. Yeah, so we go to 2.329299, so 293, 3293, 3293. Okay, and then do another one. Try the next one. And then the next start doing work. Alright, so do the next one as well. So all you have to do, now that's adding 2 extra 0. Let's see what limit it becomes. Put 2 0 there, put 2 0 there. 2.3028, 2.30285 today. Happy Pi Day. Oh, Pi Day. Yeah. Forgot about it. Thank you. All right. So 285. Okay, and then we'll keep going. What's the next one? How many 0? 1, 2, 3, 4, 5. So 2 extra. How come? Oh, I think I put too many 0. Doesn't matter. Just put one more. Let me get rid of this. 3 0. Oops. 2 3 5 2 8. Oh, it doesn't change. Oh no. 2 8. 305, 30523, 305 29, isn't it? 003, 001. 2.523. Oh, 30. Oops. Yeah. Okay. Okay, 30285. Is that right? 30285. That's what I wrote before, I think. All right, and then the last one you have 1, 2, 3, 4, 5. 3, 2 more 0. 2 more 0. Yep. Oh, you get the same thing, isn't it? Or very close. 2.3026. Yeah, 26. Okay. All right. So we're getting stabilized. So we know that it's approaching a limit, and this limit is a very strange number because it doesn't seem to have any pattern to it. So at least we know that for sure, correct to 1 decimal place about 2.3. Yes. So now we know that the derivative, going back to the formula, is 10 to the power x times this number, which is 2.3. That's the derivative of 10 to the power x. That it's going to be 2.3, approximately 2.3 times 10 to the power x. Let's write it down. 2.3 times 10 to the power of x. That's the derivative of 10 to the power x. So as you can see, it's not very convenient, isn't it? Because if I differentiate 10 to the power x, I have to remember this 2.3 number. And it's not even exact. So maybe what we do is, let's try it with another function. What if I do it with, so basically in general, if I differentiate a to the power x, we expect to see a constant k times a to the power x, isn't it? Where k is a constant. So that's what we discovered so far. If I differentiate the exponential function, there must be a constant in front of the exponential. And that function doesn't change, isn't it? It's still an exponential function with the same base, but with a constant in front. All right. So what if I change the a? What if I change it to 2? Let's see what constant we get. Okay, what if we change to 2? So We don't have to do all the working because I could just copy the same thing but change the 10 to 2. Agree? So let's do that. So if I differentiate 2 to the power x, let's write it down. So if I differentiate 2 to the power x, so dy over dx, it's going to be 2 to the power x times the limit as h approaches 0, 2 to the power h minus 1 over h, right? I mean, if you go through all the steps again, but we don't need to. We just have to change the 10 to 2. And then you just use your calculator again. Calculate this limit. See what number we get. Hopefully, maybe we can discover a pattern. Maybe there's a pattern to it. Maybe or maybe not. But we'll have a try. So press that. Press 2 to the power of 2 to the power of 0.01 minus 1 over 0.01. Get 0.69555. 0.69555. And then let's increase the number of zeros. So you still get, that will be 2 extra zeros. 2 extra 0. 0.69 again, 31. And then how about the next one? Add 2 more zeros. 0, 0. 0, 0. You still get 0.69, but 3 something. So we'll know it's getting stabilized. We'll know it's going to be about 0.69 something, right? So now we found the derivative of 2 to the power x as 2 to the power x times 0.69. Again, it's approximate because it's very long. We're not going to write everything. All right. So again, it's not very convenient. There's another number it comes out that seems to have nothing to do with the 2. You just get 0.69 times 2 to the power x. But what we know, what we could see now is that if I decrease the power, obviously that constant decreases, isn't it? Gets smaller. Compared to the other case where we did 10 to the power x, it's bigger, isn't it? It's 2.3. So this is 0.69. So it will be useful if we have a constant that's k equal to 1. That k, if I make that k equal to 1, find a base a so that the constant is 1, that's going to make our differentiation easier. Now that number is going to be somewhere between 2 and 10, isn't it? And that number is called e. So the number is e. And there's a button on a calculator that calculates e. So if you do, so e is over here. So if you press shift, this one, press 1. So you press shift, ln. So you just press shift, L. Actually, this is not a good way. It's actually next to the pi, but probably better this way. Alpha, this button, see pi, today is a pi day, we've got E. So you get alpha with this button. Alpha, this button will be times 10 to the power x. But press this button, see what number you get. So press this button, which is press equal, you get 2.718281828. 1828. Okay, so 2.71 828 1828 1828 1828. Okay, all right. So this number is called E. And like pi, actually I filled it wrong. That's why I left more space on the top. So that number is E, which is 2.718281828 and continues. It doesn't stop there. And just like pi, it is an irrational number. Okay, let's check whether it works. So this number, being very long, it will give us a constant k equal to 1. Let's try it. So let's differentiate. So if I differentiate it, it's going to be e to the power x times the limit as h approaches 0, e to the power h minus 1 over h. So we'll just try to see whether it works. Okay, using a calculator. So you just use the calculator. So press fraction alpha e to the power of 0.01 minus 1 over 0.01. You get 1.005, like that. And then do the next one. What if I increase the number of zeros? Does it actually reach 1? We'll find out. You get 1.0005. So it's really getting closer and closer to 1, isn't it? And then if we put even more zeros, you will get very close to 1. Yep, it is getting very close to 1. It's approximately 1. Right? So we'll get to 1. So this is going to be e to the power x times 1. E to the power x. So now we discover a new number that will make the differentiation exponential easy. If you differentiate e to the power x, we're going to write e to the power x. So that's what the number e comes from. Because the derivative is simple, doesn't have a constant there. And there's another button you can press to get e, which is press shift. So if you press shift ln, you get this button here. So you can press shift, shift, shift. Let me write again. Shift here, and then ln. And you'll get e. So, and make sure you put a 1 there. If you don't put a 1, it doesn't give you a number. So if you just go press shift there and then just press equal, you get error because it expects you to put some number there. So e to the power 1, you get 2.718281828. All right, any questions? So now we introduce the number e. Let's do some calculation questions. All right, so let's go to the next page. All right, do you use your calculator to calculate this? Remember there are exactly 2 ways. So to do it with the first way, if there's a power, it's easier if you just press shift that and press 0.2 because it gives you 1.22. How many significant? 3 significant, so 1.22. On the other hand, if you press the alpha one, you have to press 1 extra button. So if I press alpha E like that, you have to press the power before you enter 0.2. So you may prefer the second approach. Yeah? Alright, so we'll try the next one. So now I'm going to do shift this and then press negative 1.52 gives you 0.219, 0.219, 3 significant figures. How about the next one? 5 times that, you just write 5. You don't need to put the times symbol, just press shift that. 3, you will get your answer 100 and 0.4. So that will be significant, 100. So the 0 is counted significant. And then the next one is a fraction. Shift ln 7 over 6. You get 183. All right, any question? 183. All right, so we just differentiate it at the exponential. It's equal to itself, isn't it? Differentiate exponential is equal to itself. It's very different from the other rule that when you differentiate x power n, you actually bring the power down, right? That's a different rule, okay? These two are different because they're different functions, okay? Because their power x is the polynomial. So we're going to use this rule to differentiate the following expressions. So we're going to differentiate this. So starting with the easy one, y dash. So you want to differentiate 4 to the power ex, 4 e to the power x, to ignore the 4, and that ex become e to the power x, right? No change using this rule. So differentiate e to the power x is e to the power x. The 4 don't change like that. It's a constant. Then the rest you use the rule that you learned before, which is 10x minus 3. Finish. All right, how about the next one? You have to use the chain rule. So you see there's a bracket, you use the chain rule. So y dash is 3, 5 e to the power x minus 1 to the power 2. So differentiate the power first, followed by differentiating what's inside the bracket, which is 5 e to the power x. And if you times them together, you get 15 e to the power x, 5 e to the power x minus 1 squared. Yeah? All right, see if you can work out what to do for the next 2 cases. Now, what do we do for the next one? What rule do we use? We use the product rule. Very good. So that's U, that's V. So write down what U dash is, write down what V dash is, and times them together. So U dash equal U equal to U dash equal to 2x plus 1. V dash is equal to itself again. So Y dash is U dash V, which is that, plus UV dash. And then you will see that there's a common factor of e to power x, which you could factorize out. So factorize out e to power x. And that's quite common in product rule because the e to power x doesn't change. You often get a common factor. Collecting like terms, you will get x squared plus 3x plus 2. You can just leave it like that. No need to factorize further. Any question? Yeah. Try the next one. What rule would you use for the next one? You use quotient rule. Okay, use the quotient rule to try. Have a try. Two pages tomorrow. Okay. Okay. All right. Try using the quotient rule. So we're going to write U. That's your U. That's your V. So U dash equals to e to power x. V dash is also e to power x. So Y dash is equal to U dash V minus U V dash over V squared. Like that. So again, I encourage you, you can factorize or you can expand, up to you. Maybe this time I expand this time. Expand this, including the e to power x. And you will get e to power 2x minus e to power x, minus e to power 2x minus e to power x, or over e to power x minus 1 squared. Okay? And you need to collect like terms. These two are like terms, they cancel. And these two will be added together, which become negative 2 e to the power of x over this thing squared. Alright, any questions? So these are the rules you could use: product rule, chain rule, and normal rules. Okay, and there's more questions in the textbook we can practice. Alright, so after we do this, the next natural question to ask is to find the equation of the tangent. And that's not hard to do because all you have to do is find the derivative to find the gradient. So if I find dy dx, you get e to the power x. The gradient of the tangent is when you substitute x equal to 1 in, which is just e. And then what you do is, we need to find the y value, right? We need to find the point. So to find the point, what you do is you substitute x equal to 1 into y, which is just e, right? That's your point. Your x1, y1. So what you need to do is to use the formula y minus y1 equal to m x minus x1. Okay, do that. And then work out, okay? Yep. Yeah, let's go through it. Maybe it doesn't work, maybe it does, I don't know. Alright. Okay, so let's try y minus y1, which is e, equal to gradient x minus 1. Expand this, you get ex minus e. And then you can cancel the negative e from both sides. So you end up the equation of the tangent is y equal to ex. Question. Right, pretty easy. Try the next page when you're ready. The equation of tangent. And normal is the same thing. You just have to change the gradient. Alright. Alright, good. We won't go through further. You could try that in the textbook. Okay, let's go to the next page. Alright, so the next one is you have to prove something. Show that this is true. So what do? We find the second derivative. To find the second derivative, find the first derivative first, which is equal to 5 e to the power x the minus 2 becomes 0. And then find the second derivative, which is equal to 5 e to the power x again. And you have to show this is true. So what do? We just have to show the left-hand side, which is equal to the second derivative, 5 e to the power x. And the right-hand side is equal to y plus 2. And y plus 2 is exactly... Oh, it didn't work. Oh, no, it does work. Sorry, it does work because I looked at the wrong one. That's minus 2, right? That's y plus 2. And the negative 2 and 2 cancels. Yes, it does work. And therefore, left and right are the same. And then you write the conclusion. Therefore, the second derivative thus equal to y plus 2. All right, so this type of question can be asked, and they are not very difficult. You just need to know what to do. You just have to substitute left and right and show that they work. All right, and then we'll just do one more question, curve sketching. Then you can do the exercise 4.1 today. So we have to do a curve sketching. So curve sketching involving exponential can be a bit more difficult. So let's go through this. And these ones usually have asymptotes with it. So we're going to follow this usual procedure of finding the derivative, find the stationary point, and the point of inflection, or the information before I draw the curve. So let's start with that. So we start with y equal to 2x e to the power x. Now find the first derivative using the product rule. Okay? Use the product rule to find the first derivative. So u is 2x and v equal to e to the power x. And then also write down u dash is 2, v dash is e to the power of x. Alright, use it to find the first derivative and then make that equal to 0 to find the coordinates of the stationary point. And then also find the second derivative to find the inflection point. And then we're going to sketch the graph after this. Okay, have a try. I don't know, we're going to go through. Yeah, should be right, I think. All right, let's go through this. So we get u dash, which is 2 e to the power x plus 2x e to the power x. And then we factorize the 2 e to the power x out. You get x plus 1. Like that. Make that equal to 0 to find the stationary point. So you have two equations. So you get 2 e to the power x is 0, or x plus 1 is 0, right? Now, first one is e to the power x is 0 over 2, which is 0. Now, e to the power x equal to 0 have no solution. So every time exponential equal to 0, no solution. Okay? And the question is, why is it no solution? Because if you draw the graph of exponential, it looks like this, right? It never cuts the x-axis, so it has no x-intercept, right? So no solution. It doesn't cross the x-axis. That's why no solution. Whereas the other one, you get x equal to -1. So after you do this, you're going to find the y value. So how do you find the y value? Substitute -1 back into the equation. Y equal to 2x e to the power x. Y equal to 2 times -1 e to the power -1, which is -2 e to the power -1. Okay? So that's your stationary point. Okay, that's your stationary point. And we're going to determine the nature because we're going to find the second derivative anyway to find the point inflection. Let's find the second derivative to determine the nature. So going back to the first derivative, I will use this one here rather than the first one. Use this one to find the second derivative. Use the product rule. Okay? Alright. So start off with y dash is 2 e to the power x. And then find out y double dash. Okay? Have a try. So find the second derivative. Alright, find the second derivative. Is product rule. Continue with that. So we get 2 e to the power, we differentiate the first, leave the second, and then leave the first, differentiate the second one. And if you do that, there's a common factor of 2 e to the power x. And sort of maybe you see a pattern there, x plus 2, right? Okay, now we substitute -1 to determine the nature. So if I put x equal to -1, which is this bit here, y second derivative equal to that, -1 plus 2. Use your calculator to see what you get. You should get a positive number. If not, then try again. Shift that one, -1, bracket. Yeah. Oh, it's a bit late, sorry. Yeah, I will do that right now. And then I have to pause this. So check what the nature of the stationary to record, and then unfreeze. Okay, good. All right, so what answer did you get? You get 1 there, equal to 0.735, 0.73, and that's positive. So you say, therefore, it is a minimum. So this is a minimum turning point. All right, so after we do this, we now have to find the point of inflection. How do I find point of inflection? We make point of inflection. So what you need to do is to make the second derivative 0. So you get 2 e to the power x, x plus 2 equal to 0. And again, like before, you have two factors. This equal to 0, you know that's no solution. And the other one equal to 0, you get x equal to -2. Now with point of inflection, you have to do a test. You have to do this first. So do a test first. Usually you work, but you just have to do a test to confirm that. So do a test. That will be 0 and substitute -1, -3. Yeah, okay, have a try. So you do have to write down the values. So let's see. So if I substitute -3, you get 2, shift that, -3, bracket, -3 plus 1, close bracket, you get -1.99, so negative 0.2, -0.2, and the other one substitute -1 as well. So change the 3 to 1, and then you get, oh, that's a 2, sorry. Oh, so I must have got this wrong then. 0.3. Ah, okay, so if I put 3 again, let's try 3 again. Alright, -0.1, -0.1, okay. -0.1, and then we'll go to the next bit, go left, we'll go up, okay, 0.7, 0.7, so therefore it is concave down to concave up. There's a change of concavity. You must show there's a change of concavity to get the mark for the inflection point. And then you have to find the y value. So to find the y value, what do? You have to go y equal to 2x e to the power x, substitute -2 in. So y equal to 2 times -2 e to the power -2, so it will be -4 e to the power -2. So it's -2 comma this. Alright, so we've got this information. Maybe you should highlight this information. There's an inflection point. There's a minimum turning point, which we're going to use, okay, to draw the graph. Alright, so we're going to go to the next page to draw the graph. So -2, -4 e to the power -2. The other one is -2 e to the power of -1. Okay, let's write them down on the next page. So the minimum turning point, oops, that's a 10 here. Okay, let's write down the minimum turning point. Minimum turning point is this one here, -1, comma -2 e to the power -1, and then the inflection will be -2, comma -4 e to the power -2. Alright, so just remember it concave down, then concave up. That will help you to draw the graph. Okay, let's draw the graph. Actually, before we do that, let's find the x and y intercept. X and y intercept. So let's start with the x-intercept. So we get y equal to x e to the power x. So to find x-intercept, make y 0. Put 0 there, like this. So therefore, either 2x is 0 or e to the power x is 0. 2x is 0 means x is 0, and again, hopefully remember, this is have no solution. We found the x-intercept. How about the y-intercept? Y-intercept is substitute x is 0. So you get y2 times 0 e to the power 0, which is 0. Okay, so y-intercept 0, x-intercept 0. We're almost ready to sketch the curve. Let's draw the graph. I could use this. Okay, let's draw the graph. Okay, so we'll draw a vertical line and then draw a horizontal line. Yep, that's good. And then we go back to this. All right, let's try to draw it. Okay, all right, let's plot the points. Now, with these points, it's not really useful to us because I don't know how big they are. So one way to do that is just use your calculator to do that again. -2 e to the power of -1. So it's about -0.73, 0.74, negative 0.74, and then the other one will be -4 and a 2. So that's, I think, even smaller, negative 0.5. Negative 0.5. Okay, so remember these numbers. That's going to help us. Okay, we're ready to sketch. So maybe space out your one a little bit further. So put one here, put 1, 2 there, like that. Something like this. Yeah, okay. Actually, don't put the numbers because it's going to block the points. Okay. Of course, label the x, label the y. Okay, starting with the first point, it's negative 0.74. So put your 1 here, like that. That's -1. So at -1, it's -7.4. So around about here. Right, around about here. So please indicate the coordinate, -1, -2, e to the power -1. Write down the coordinate of the stationary point. H is a minimum. Just draw a little minimum there. Gonna look good, so I draw again. Right. And then there's an inflection point somewhere at -2, which is this, about -0.5. So halfway through, so about here. So again, label the coordinate, -2, -4, e to the power -2. All right, good. And you have an x-intercept of 0, origin. Okay, let's join the point. So let's use green. So it's going to go like this. And this is going to be concave up, right? Because on the left of 2, it's concave up. Then on the left of -2, it's concave down. So how do I draw this with concave down? What we need to do is we have to examine the limit as x goes to -infinity for this function. And how do I do that? You just have to substitute big values on your calculator. So with this exponential function, you often get horizontal asymptote. So let's substitute x equal to 1,000 or 1,000, okay? Or maybe if it's too big, maybe just 100, right? Just 100. I think 1,000 will be too big. Times 100. Shift that. No. Shift that 100. Yeah, you get this, which is actually -100. -100. -100. Okay, -100. Negative. Okay, get that? So it's 10 to the power -42, so it's very small. And if you increase more, so -200, it's getting even smaller, right? So it's getting close to 0. It's approaching 0. So there's a horizontal asymptote here. Let's do it in red pen. There's a horizontal asymptote. So it's going to concave down. So it's going to go like this. Concave down, right? Let me improve this graph a little bit. So this point here is a stationary point minimum. So it can, something like this, it's minimum, but I think I went a bit too flat. Yeah. Okay, something like this. So it's like this, and then like that, right? Something like this, okay? Yeah. And you can examine when x goes to positive infinity, that's going to go to infinity. So you keep going up like that, okay? So you can check that later on with a calculator. All right, so the graph is drawn. What else I want to say? All right, let me leave that table next time. Okay, I will talk about that table next time. Okay, good. So you can start the exercise 4.1. There's enough time to do maybe 10 questions, 10 derivative questions. Let's stop the video.